Crane Naval Surface Warfare Center has been the leading research and development center for the U.S. Navy since their creation during World War II. They have developed many of the current weapons and ammunition used by our soldiers today in combat. Crane has asked our group to develop a method of measuring the velocity of a bullet while it is inside the bore or the barrel of the gun. This project is important because it could help us understand how bullets behave inside the barrel, and this could lead to changes in bullet caliber, bullet dimensions, and also help Crane to compare different types of bullets, such as tracer rounds or armor piercing. Our group chose to use strain gauges to measure bullet speed. When a bullet is fired, the bullet produces a small amount of outward strain on the wall of the barrel as the bullet travels forward. Strain gauges output a voltage reading based on how much strain the gauge is experiencing. If the voltage increases, the gauge is reading more strain. Here's our rifle with 4 strain gauges mounted to the barrel. Now as the bullet passes down the barrel, it causes a spike in the measured strain. By finding the time that this spike occurs, we can find the velocity using the basic equation velocity equals distance divided by time.
First, we started by attaching strain gauges to the barrel. What we did is we attached the strain gauges with some super glue and then taped them to prevent excess movement from tearing off the strain gauges. This was because during movement of the barrel and the gun, a few times strain gauges would get ripped off and we had to prevent that. Now, going on to our circuit, those strain gauges change resistance values as the bullet passes. Now we have 2 strain gauges per point, and so in our circuit we have half bridge, and that change of resistance values causes a change in voltage across the bridge. We have amplifiers in the circuit itself to pick up that change in voltage and amplify it on the way to the DAC, data acquisition system, or DAC.
From our circuit, these cables come down here to the DAC board, or data acquisition board. They go into these ports along here, and then from there they come up to the computer where we analyze the signals sent from the circuit board into the DAC using MATLAB.
So any data that you're measuring, you're going to need verification if it's a new system. What we used for our verification was a chronograph and a high-speed camera. We found a way to sync the high-speed camera with our measurements to make sure that the bullet was leaving at the same time as we were measuring it leaving. And then we compared our calculated velocities to the chronograph to make sure that we were getting accurate times and speeds.
I am in charge of the high-speed camera. Once everybody said they're good, I click go and give a thumbs up to the MATLAB technician.
I initiate the MATLAB program on the computer and then give the thumbs up to the spotter.
After that, I tap the shooter on the shoulder.
I pull the trigger.
The data from our tests is then graphed and analyzed on a computer. To verify our times, we check the high-speed camera to see when the bullet exited the barrel. After finding the change in time, we are able to calculate and graph a velocity. Shown here are the velocities compared to our chronograph readings for tests 1 and 2. Using this method, our group was able to successfully measure the velocity within 20% uncertainty. With access to faster measuring equipment, this accuracy could be improved. Our group learned a lot doing this project, and we would like to thank all of the teachers at Trine University that helped us out along the way.